All right, guys, final PowerPoint of the year. And if you remember last chapter, we were doing flow across in three-dimensional space. This chapter is all about flow along in three-dimensional space. So a lot of the ideas in this chapter are things you're already familiar with. We just have to adapt them to three-dimensional space. So we're going to follow a pretty similar process to last chapter. Remember last chapter, we took what we do about flow across in two-dimensional space, so basically the Gauss-Green theorem, and then and divergence, and then we adapted that to three-dimensional space, and we got the divergence theorem, and it was a tool for computing flow across a closed surface in three-dimensional space. There's the formula that you'll see in more traditional calculus textbooks. And we have to do the same thing for this chapter. So just like last chapter, we had to adapt 2D flow across to 3D flow across. For this chapter, we need to adapt two-dimensional flow along to three-dimensional flow along. Now, there is going to be a difference. In lesson 12, we were doing flow across typically a closed surface. So you're imagining like a sphere or a box or something and flow across that. For lesson 13, we're going to do flow along a curve, but living in three-dimensional space. So there is a difference there. I don't know if you remember, but it was a hard transition for you guys to switch from saying the word curve to switching to the word surface. Like every time you'd be like, oh, the flow along the curve, and you'd have to like backspace and then change it to surface. Now you can go back to saying curve again. It's going to be flow along a curve, but a curve living in three-dimensional space. Anyway, probably the best way to build up to this is first by talking about how to do flow along in 2 dimensions with an open curve. So let's go back in time to 2-dimensional space. And we had this really simple formula for a path integral. We just did the integral of field.tangent dt. Now, you might be wondering, remember, there was this whole unit tan ds thing, and the ds is confusing, and the unit tan thing is confusing, but then the formula that we actually use is not confusing, because the formula that we end up actually using is not the unit tangent, and the differential is not an s but a t. I could show you really quickly where that all comes from, because it might help you in the three-dimensional case with not getting confused. So first of all, ds is an integral with respect to arc length. And so if you imagine a tiny little piece of arc length ds, that arc length is built out of a little change in x and a little change in y. And so if you were to do Pythagorean theorem on that, you would get that ds is equal to the square root of dx squared plus dy squared. You guys with me so far? Does that make sense? Yeah. Now, if you make this all, if you kind of mess with some dt's here, you could say that ds dt is equal to the square root of, I could write dx dt, or you could just write that as the more standard x prime of t, and then squared, plus y prime of t squared. Why am I showing you what ds dt equals? Well, that might help us change to a dt integral, because you could think of ds as dt times ds dt. So if I want to switch from a ds integral to a dt integral, basically I have this square root of the x prime of t squared plus y prime of t squared. Well, wait a minute, unit tangent in its denominator. I wish I had a little more space here. I would do it on the whiteboard, but I kind of want it in these, captured in these notes. It would be easier to do this on the whiteboard. But anyway, unit tangent is x prime of t comma y prime of t divided by the magnitude of that vector. So divided by the square root of x prime of t squared plus y prime of t squared. Long story short, what you'll see is the denominator from unit tangent crosses out with this numerator from ds dt. And so when you switch from a ds integral to a dt integral, unit tan just turns into the tangent vector. If you're confused by that, don't worry. It's not super important. The main thing to remember is you're going to see the word unit tan floating around this chapter. But realistically speaking, anytime you're actually crunching numbers, anytime you're actually like doing a calculation, you don't need to worry about the word unit. It's just going to be the tangent vector. It's going to be the tangent vector dt when you do these path integrals in three-dimensional space. All right, let's keep moving here so I don't run out of time. So again, here's the three-dimensional formula for doing a path integral in three-dimensional space. Technically speaking, there's this fancy-looking formula, the integral of field dot unit tan ds. You'll probably never, ever use that. And typically, you're going to do the second version, the integral of field dot tangent dt. Just a regular tangent vector, not a normal, not a unit tangent vector, just integral of field dot tangent dt, just like we've done every other time in this class. And if that integral ends up positive, you know the net flow of the vector field along the curve is with the direction of parameterization with the tangent vectors. If that path integral ends up negative, the net flow of the vector field along the curve is against the direction of parameterization, against the tangent vectors. This is for a curve in three-dimensional space, not a surface or anything. You guys good with it so far? Yeah,
Why
Dean.
isn't it for a surface?
So it's not that we can't do this sort of calculus for surfaces and for other higher dimensional objects, but think about clockwise and counterclockwise for a second. It's a lot easier to talk about flow along a closed curve being clockwise or the flow along of a vector field along a closed curve being counterclockwise than it is for talking about surfaces. So I mean, all of this calculus generalizes to higher dimensions, but we're keeping it in, you know, like a level that we can kind of picture what's going on. That's all. Yeah.
Wouldn't a surface just be the summation of every single, like, go around of like every single kind of curve? Like,
Yeah, you could generalize this calculus to any number of dimensions and to other kinds of objects, but spend a few minutes thinking about like flow along a cube for a minute, or flow along, like it's not necessarily easy to picture. So this is just a nice frame of reference. Like we're sticking to a geometric object that we can picture what's going on. So guys, let's do a really simple example. Let me do a problem that could appear on a quiz, and it would be a fairly simple problem. So I've got a curve parameterized in three-dimensional space, t, comma 2t, comma 4 cosine of t. I have bounds for my parameterization. T goes from 0 to 2 pi. Those will turn into limits of integration for my path integral. And I've got a fairly simple vector field. I was trying to keep it simple, so I went with negative z, comma x, comma y. And then it says find the net flow of the vector field along the curve. So first of all, the official formula is field dot unit tan ds, but we don't really like doing computations with that. We would prefer to turn it into the integral of field dot tangent dt. And really, this entire problem boils down to substituting stuff in. So field of x of t, y of t, z of t means taking the t and the 2t and the 4 cosine of t and plugging them into the vector field. You have to be a little bit organized to do it, but you get negative 4 cosine t, comma 2t. You're kind of just plugging into negative z and x and y. You're plugging in z of t and x of t and y of t there. Anyway, and then the tangent vector is easy to calculate. You take your t, comma 2t, comma 4 cosine t, and you're just taking your derivatives with respect to t, and you get 1, comma 2, comma negative 4 sine. Evaluate that dot product, and finally we get down to a single integral that you guys could have computed without any trouble, like last year. You get 16 pi plus 4 pi squared is your answer. Be careful, do not summarize this as clockwise or counterclockwise. I realize that this is a positive result, and I realize the temptation would be to say that the net flow of the vector field along the curve is counterclockwise, but it's not counterclockwise, it's with the direction of parameterization or with the direction of the tangent vectors. Clockwise and counterclockwise don't have any meaning for an open curve. So, guys, any questions? All right, let's keep cranking here. So we talked about how to do this for an open curve. Now we should probably talk about a closed curve, but a closed curve is more subtle. The words clockwise and counterclockwise those are a little bit harder to define in three-dimensional space. And there's a couple other little features of closed curves that we have to be careful with in three-dimensional space. So the next few slides are mostly about dealing with subtlety, dealing with basically what does it mean for us to have rotation in three-dimensional space, and what does clockwise counterclockwise mean when you're in three-dimensional space. We have to deal with those two subtleties. Once we have those taken care of, then we can come up with what's going to be called Stokes Theorem. It's going to be our three-dimensional analog of the Gauss-Green theorem, our three-dimensional generalization of Gauss-Green theorem. So anyway, let's look back in time real quickly. Here's a previous chapter where we were measuring the net flow of a vector field along a closed curve in two-dimensional space. And remember, we had choices. The whole point of the Gauss-Green theorem was to have two options. Either we could do the path integral along the boundary, or we could do the double integral over the interior. The two challenges we're going to have to handle is we want to be able to use words like clockwise, counterclockwise. How do we generalize those to three-dimensional space? And remember that in two-dimensional space, we were double integrating the rotation of the vector field. Well, what does rotation mean when you're in three-dimensional space? Once we have those taken care of, we should be good to go. Let's take care of clockwise, counterclockwise first. So in 2 dimensions, defining what clockwise means and what counterclockwise means is really simple because everybody looks at the same plot from the same vantage point. The XY plane is a flat sheet of paper, and everybody looks at that sheet of paper and can easily agree on what clockwise or counterclockwise means. Let me give you an example where that's ambiguous if you're in three-dimensional space. So suppose that someone is standing up at the North Pole on Earth, and they decide to do a little dance where they are twirling in the counterclockwise direction. So they're kind of like twirling around and around and around. And then they call their friend on the South Pole and they say, hey, I'm twirling in the counterclockwise direction. For the person on the South Pole, what does that mean to them? Yeah, relative to their position, that's a clockwise twirl, but relative to the person at the North Pole, it's a counterclockwise twirl. So basically, you need a common frame of reference to agree on what clockwise and counterclockwise means in three-dimensional space. Let me show you another quick example. So I have a closed curve here with an orientation. You could see some tangent vectors. And then I have like an interior surface as well. And that interior surface has that blue curve as its boundary. Would you guys define those red vectors as going clockwise or counterclockwise? From the most typical vantage point, counterclockwise, I agree. But remember that in mathematics, like on Earth you have gravity, and so you kind of, you'll look at a plot and you'll have an instinct about what's top and what's bottom. But if you're like, say maybe you're a Spider-Man instead of just a regular human, then either of those vantage points is equally valid, right? Now where Spider-Man is standing right now, is that rotation going to be clockwise or counterclockwise relative to his position? He's going to call that counterclockwise, but he's Spider-Man, so he's not stuck at the top of that surface. If he wanted to stick on the bottom, now what would you say that orientation is? Clockwise, exactly. So many of the problems that you guys are going to be doing, the very beginning of the problem will involve plotting a normal vector and saying, hey, let's all agree that the place that I plotted this normal vector is going to be defined as the top of the surface. Now, the word top is not going to have to agree with gravity, right? There's no gravity in a three-dimensional plot. So you could put the quote-unquote top of the surface anywhere you want. But you need to start these problems by saying, hey, I plotted a normal vector. Let's call that the top of the surface. And relative to that normal vector, this curve is parameterized, hopefully in the counterclockwise direction. Right? Typically, we are picking tops of surfaces so that they point in the... we are picking tops of surfaces so that our curve is oriented in a direction that we would call counterclockwise. The right-hand rule will help you with this. So if you're ever trying to figure out, like, wait, where should I put my normal vector so that my curve, we could call this a counterclockwise parameterization, do the right-hand rule. Take your right hand, point your thumb with your normal vector that you want to plot, and then make sure that the tangent vectors agree with your fingers. And then that's a really good way to define, to figure out where to put your normal vector in order to have a counterclockwise parameterization. Be careful with this. Every year I'll have a student on the quiz who will think that you could solve path integrals with the right-hand rule. The right-hand rule is not a calculational tool. The right-hand rule doesn't do path integrals for you. So your right hand will not tell you the net flow of a vector field along a closed curve. What the right-hand rule does for you is it's a good way of figuring out where to define the top of your surface so that your curve has a counterclockwise parameterization. But it doesn't do anything to the vector field, right? So don't use it to solve problems. Use it to set up problems. Maybe that's a good way of describing it. The right-hand rule doesn't solve any problems for us. It helps us set up problems so that we can solve them. We also have to be a little bit careful. Everything I just described is predicated on what's called having an orientable surface. An orientable surface is a surface that has two sides to it so that we could call one side the top and one side the bottom. In three-dimensional space, you can have surfaces that can't be oriented. For example, if you guys want to take out a sheet of paper right now, like an old piece of scratch paper, I'm going to have you make a Mobius strip real quick. The way you make a Mobius strip is you take out a strip of paper. Instead of just making it into a cylinder, right before you join the pieces together, just put a quick little half twist into the paper. And what I want you to do is take your finger. Hopefully you guys will actually make one of these. I mean, it's a good idea. Trace your finger along the Mobius strip, and as you're tracing your finger along, what you're going to notice is you're going to traverse the entire Mobius strip without ever having to flip sides. Whoa. It's a lot more believable if you do it with your own finger. If you're trying to watch my finger, so you take your strip of paper. First try making just like a bracelet out of it. So that's just a cylinder. So when you join them, right before you join them together, on one of them, just do a quick little half twist. And then, yeah, if it's just got a little twist to it, yep, that's a Mobius strip. Yeah, yeah, you might have needed a longer strip, but yeah, here you could have mine. Here you go.
Thank you.
Anyway, guys, like imagine you're an ant walking along that Mobius strip. What you'll notice is that ant will get to every part of that Mobius strip without ever having to flip sides. It leads to a crowd-pleasing joke that you are welcome to use in any social situation. I guarantee it's a hit. Why did the chicken cross the Mobius strip? No, to get to the same side. It only has one side. There is no other side. There's one side. Yeah. Sid, you can use that one for free. That's yours now. You don't even have to give me credit.
Okay.
Family parties, first dates, speeches at weddings. It's always a hit, always a hit. Anyway, guys, so look out for Mobius strips. Basically, if you end up with a Mobius strip, you can't do the problem using Stokes theorem. So the theorem that we're about to construct, you're not going to be able to do Mobius strips problems with Stokes theorem. Stokes theorem is not going to work. All right, so here's a little Q&A that should help us keep us moving here. The clockwise problem in three-dimensional space, we easily fix that by starting every problem by designating a top side of our surface. Use the right-hand rule to figure out where you would put the top of the surface. The word top doesn't mean that it has to be oriented with the positive z-axis. The word top means like put a normal vector in, call it the top of the surface, and make sure the right-hand rule then says that your curve is parameterized counterclockwise. If you don't have a top side, like if you have a Mobius strip, a non-orientable surface, we're in trouble. So that's the second part of the Q&A. There are times we're in trouble. I just can't really do the problem. And then finally, we have to generalize rotation from a two-dimensional idea to a three-dimensional idea. I didn't really talk too much about this yet, but think about it. In two-dimensional space, there's only one plane of rotation. In two-dimensional space, the only way to rotate is on the xy plane. And so it's like very simple thinking about rotation in two-dimensional space. In three-dimensional space, suddenly rotation, there's three different planes that you can rotate in. If you've ever tried to like fly a drone or or done like an airplane simulator, or if you've actually flown an airplane, you'll be familiar with this. If you've ever kayaked, you might be familiar with this. I was on a kayaking kick when I made these notes. Maybe I should switch to airplanes because I feel like that's maybe more familiar to people. Or if you've ever played a video game where it's like with flying a spaceship and it's like first person, you'll be familiar with all this stuff. So a kayak can rotate in 3 different planes because a kayak lives in 3-dimensional space. The simplest kind of rotation, this will happen if you're a beginner and you're not a very good kayaker. Typically one side of your body is stronger, or one side of your body has a better stroke than the other side with your paddle, and you'll end up just like spinning in circles on the water. That's surface rotation, right? That's XY rotation. It can also happen if there's like a whirlpool underneath you or something, or if the rudder on your kayak is off, you'll like spin in circles. Surface rotation. If you're ever going to be a competitive kayaker, or if you're ever going to do like whitewater kayaking, one thing you need to learn how to do is an Eskimo roll. It's a good way to not die, because if you're on unstable water, you could end up flipping your kayak, either to your left or to your right. And so when you get good at kayaking, you have to learn how to throw your body weight to finish that Eskimo roll and then come back up again. That's YZ rotation. And then the scariest one, this is the one where this is really deadly if you get stuck in a hydraulic or a hole. That would be where there's like a big rock underneath the river, and it's causing like a forward rotation, and your boat gets stuck in like an infinite forward rotation. People would drown to death from that. That's XZ rotation. With an airplane, I think that XY rotation is yaw, right? And then I don't remember what YZ rotation is, and then XZ rotation is pitch, right? So there's, yeah. Well, actually, with an airplane, you could do an Eskimo roll too, right? So anyway, there's, what's that?
So that's like where you're going like.
Yeah, the one that's going on with those Boeing airplanes right now.
So wait,
This XZ rotation is what's happening with those Boeing airplanes.
It's like the kayaks doing the somersault, right?
Yeah.
Okay.
Yeah. Yeah.
Oh, I don't like that.
The barrel roll might be the same as this one. I'm not really sure though. I'm not very familiar with airplane terms. I should look it up though. I might change out the kayaks for airplanes. I think more people will be familiar with it. Guys, my point here though is when you're in 3-dimensional space, rotation needs to be a vector quantity, because we need to store information about rotation in 3 different possible planes of rotation. So the rotation of the vector field for 2-dimensional space was scalar. To go to 3-dimensional space, our idea of rotation needs to be vector. It needs to have 3 components for the 3 different planes that you can rotate in, which makes this chapter fundamentally more difficult than flow across. With flow across, the divergence of the vector field, that was going to be a scalar quantity because we have del dot f right there, right? We take del, we take the vector field, we take their dot product, that gives us the divergence of the vector field. Guys, what's the other operation that we like to do between 2 vectors in 3-dimensional space that's not the dot product?
Cross product.
The cross product. And the cross product doesn't produce a scalar like the dot product does. The cross product produces what? A vector. So the cross product's going to be perfect for us. The cross product is going to be a great way to define what we're going to call the curl of a vector field. This is all really good information to take down into your notes. You guys are going to be responsible for understanding this stuff. How you memorize it is going to be up to you. If you really like just making flashcards and just memorizing certain letters in a certain order, this last part of the formula might be something you want to memorize. I am not good at this. I am not good at remembering, like, wait, what came first, P or N? Wait, was it dP dz minus dN dy, or was it dP dy minus dN dz? Right, like, I just get too mixed up with those letters because they're not meaningful to me. So I am better with, like, when I memorize this stuff, I just remember that the curl of a vector field is del cross f. And then I just compute that 3 by 3 determinant. Now, what you'll find by the end of the chapter, it probably doesn't matter whether you like doing flashcards or whether you like memorizing ideas, because you're going to use the curl so many times, you're probably going to end up pretty much having it memorized in whatever form that you chose to memorize it in. But the point here is the curl of a vector field is a cross product of del and the vector field. It's a 3-component vector. And guys, what do you notice about, say, the z coordinate of the curl? The z component of the curl. Does that look familiar? It looks like the rotation of the vector field from xy just xy space. Guys, would you say that in addition, the other 2 components also look like similar, at least, to rotation? Yeah, it's essentially the rotation of the vector field, but in the 3 possible planes where you can be rotating. So I can kind of show this off to you. Look in this next slide. I can really show you what I mean by that. So here's the equation for the curl of the vector field. Look at the x component of the curl right there. Well, the x, basically we're talking about rotation that's going to be perpendicular to the x-axis. Well, what plane is perpendicular to the x-axis? The yz plane. So you can kind of use the right-hand rule here to picture it. The x component of the curl causes rotation to happen on the yz plane. Similarly, the y component of the curl causes rotation. Basically, it's rotation that's going to be perpendicular to the y-axis, right? It's in the y component, so it's rotation perpendicular to the y-axis. And, well, perpendicular to the y-axis is rotation on the xz plane. So the y component of curl causes swirl on the xz plane. And then finally, the z component there causes swirl on this. This is why it looks like rotation. If you're talking about rotation that is perpendicular to the z-axis, well, what plane is perpendicular to the z-axis? The xy plane is perpendicular to the z-axis. So the z component of the curl causes swirl on the xy plane. By the way, if you guys ever look at a textbook from a, like a more traditional calculus textbook or notes from a different calculus course, they don't use, that quote-unquote rot field, the rotation of the vector fields that we saw in a previous chapter. You'll never see that notation anywhere else. Typically, you just call it all curl, 2-dimensional curl, or this is 3-dimensional curl. So just keep that in mind. If you ever look at like Wikipedia or another textbook, curl is a common phrase. Rotation is less common. All right. One thing to be careful of is the curl is a vector quantity, which means that interpreting the curl is harder than interpreting rotation. In addition, interpreting curl is harder than interpreting divergence. Rotation and divergence are scalar. Curl is vector, which means that if you plug a point into the curl, you're not going to get that much information out by plugging that point in. If you have a point x0, y0, z0, plugging that into the curl on its own doesn't tell you very much. You need to dot product the curl with some sort of reference vector of some sort, some vector that you are interested in, and that the sign of that dot product is what's meaningful. So if you take curl at a particular point and dot it with a vector, if that's positive, that means that the vector field delivers a counterclockwise swirl to that vector. Similarly, if you take the dot product of the curl and some given vector and you get a negative quantity, that means the vector field is delivering a clockwise swirl to that vector v at the point x0, y0, z0. And finally, if the dot product between curl and some given vector is equal to 0 at a particular point, the vector field is delivering no swirl to that vector at that particular point. This is confusing when you first start writing it down, but when you see an example with it in a minute, it's way better than you would think. So let's do a problem with this. This is going to be like your early on try it problems. So you're going to see stuff like this, whether it's try it 1 or try it 2. Early on, this sort of scenario will pop up. You'll be given a vector field. In this case, I just made up negative z squared x squared y cubed. And then the vector that you have is also usually given to you. So as given information, I'm saying, hey, suppose we have a vector 235 divided by its own magnitude to make it into a unit vector. And suppose that we are interested in the point in space 1, 0, -1. Well, what we're going to do is we're going to interpret the meaning of this dot product. So hopefully by the end of this slide, you guys will have a good conception of why it is meaningful to take the dot product between the curl and that vector at the point 1, 0, -1. All right, so first of all, let's just use the formula for curl to compute the curl of this vector field. This is a calculation you guys need to get good at. Now remember, I don't like memorizing the finalized formula for curl. I always feel like I'm prone to mixing up a letter of the alphabet, so I much prefer to just compute it like this. I know that the curl is del cross f, so I'm going to put ijk along the top row. I'm going to put del across the second row, and then I'm going to put the vector field f across the third row, and I'm going to take that determinant. And I'll get 3y squared minus 2z comma 2x. You can compute it any other way you want. Now I'm going to find out what the curl of the vector field is at the point 1, 0, -1. This is where people make mistakes. Bryce, give me just 1 minute. I'm going to finish my spiel, and then I'm going to get your question. Guys, the curl at 1, 0, -1, 1, 0, -1, students will see 0, 2, 2, and they'll be like, oh, it's positive. Therefore, the curl delivers a counterclockwise swirl. Guys, can a vector be positive or negative? No, only scalars have the property of like a positive scalar value or a negative scalar value. A vector can't have, by definition, a vector can't be positive or negative. So that 0, 2, 2 on its own is not a very meaningful quantity. We're really only halfway done with the problem. We can't do much with that 0, 2, 2 until we dot it with some other vector. So now for part 3, I'll take that 0, 2, 2 and I'll dot it, take the dot product with the vector that we were given at the beginning of the problem, and now we get a scalar. And guys, would it be fair to say that that scalar we get is positive? Yeah. What that means is the vector field is delivering a counterclockwise swirl to the vector v at the point 1, 0, -1. So in order to do anything with the curl, you need to take a dot product with a given vector, and then that will tell you what the vector field is delivering to that vector. So a positive result tells us that the vector v experiences a counterclockwise swirl around it at the given point 1, 0, -1. Bryce, you had a question?
Does your vector have to be a unit vector?
No, it's just typical that it is. So I made it a unit vector just because I think on your homework, the triad problem you're going to do, I think, was giving you unit vectors. Okay. But no, a dot product will come out. So if curl and a vector have a positive dot product, then curl dotted with the unit vector of that original vector will still have the same sign. It'll still be positive or negative. Yeah. Guys, any questions, thoughts, concerns? Okay, let's keep cranking here then. So here's the big formula for this chapter. We've kind of built up to it. We've taken care of all of the little subtleties that we care about. So say you have a 3D vector field. Suppose you have a surface R that is orientable. It has a top side and a bottom side, or at least it has two sides that you can designate as top and bottom. Well, then an orientable surface will have a boundary curve C. And you could typically parameterize that boundary curve. We're going to make sure that we define everything so that that boundary curve has a counterclockwise direction. So we're going to designate top and bottom on our surface so that we could call that parameterization counterclockwise. We also want to make sure that we have no singularities on our surface. Then we get what is called Stokes Theorem, which is a correspondence between a path integral and a surface integral. The surface integral along the boundary is equal to, the path integral along the boundary is equal to the surface integral over the interior surface. And here we have curl dot top unit normal instead of rotation there. This formula is a little mystifying at first, but I could do a couple things that might make it a little bit more believable. For example, I could show you that this Stokes theorem, if you restrict yourself to two-dimensional space, Stokes theorem just turns into Gauss-Green theorem. So this is just an extension. Well, you can either think of Stokes theorem is an extension of Gauss-Green to three-dimensional space, or you could think of the Gauss-Green theorem as a special case of Stokes theorem. But so this is a little scary. The more calculations we do, the more believable it's going to be. So let me show you. First of all, though, let me show you the notation that you might expect to see if you take this course at a different college, or if you continue on with math and Stokes theorem comes up again. Remember that previous notation is very U of I specific, so you probably won't call it field in any other course. You probably just call it F. Similarly, you probably wouldn't write out the word curl field. Writing out the word curl field is nice when you're in Mathematica, but the more traditional calculus notation is del cross F. And then you probably wouldn't write out top unit normal. You would write just dot n. So that's probably how you would see that in a more traditional course. You guys good so far? Okay, so first let me show you that this Stokes three-dimensional theorem really is the same thing as Gauss-Green theorem in 2 dimensions if you restrict yourself to 2 dimensions. So let's go back in time. Let's pretend we're just doing a problem we could have done months ago with a 2-dimensional vector field. So an m of xy comma n of xy. Well, if you really want to, you can embed a 2-dimensional problem into 3 dimensions without any issues coming up. So I could take my m of xy comma n of xy and I could put it into 3D by just saying, oh, okay, m of xy comma n of xy comma 0. So all the rotation is happening on the xy plane, and then nothing's happening, in the z direction. Well, let me compute curl now, because now I have a 3-dimensional vector field. So now I can compute the curl for that 3-dimensional vector field. And literally, you just use the formula. So ijk across the top, ddx, ddy, ddz across the middle. This is the definition of curl. And then technically it's m comma n comma p, but that p is 0 in 3-dimensional space. So anyway, when you evaluate that expression, you get 0 comma 0 comma dn dx minus dm dy. And you guys remember that dn dx minus dm dy, we had a name for that. We called it the rotation of the vector field. So our curl is 0, 0 rotation. Now the other thing you want to imagine is pretend your region R is a 2-dimensional region sitting on the xy plane. Well, if you have a 2-dimensional region sitting on the xy plane, what is a normal vector to that? Well, if it's, it's hard for me to draw it well, but if you have a 2-dimensional region sitting on the xy plane, the normal vector to that piece of surface is just pointing straight up. Well, pointing straight, a unit normal vector that's pointing straight up in the z direction is 0, 0, 1. So let's plug that curl and that top unit normal into this new Stokes theorem that we were messing around with. And when you take this dot product, this curl dot this normal vector, okay, well, 0, 0 rotation dotted with 0, 0, 1 just becomes rotation. It's the Gauss-Green theorem. Stokes theorem, when you restrict yourself to 2-dimensional space, is just the Gauss-Green theorem. Gauss-Green is a special case of this new theorem. Guys, any questions so far? Okay, let's keep cranking through this then. So using Stokes theorem, a lot of times Stokes theorem is just for some good shortcuts. So let me show you a cool shortcut. So this is a fairly complicated looking setup because you have this boundary curve. Your boundary curve has tangent vectors. You have an interior surface. You've got a vector field in 3-dimensional space. It's easy to get yourself overwhelmed with everything. But when you compute the curl of this particular vector field, you should immediately be able to relax a little bit because you see that the curl of this vector field is 0, 0, 0. So most of this complicated setup is less scary than it looks because now we have a vector field with no singularities. The curl of this vector field is 0, 0, 0. So when we invoke Stokes theorem, this path integral that we want to compute is equal to the surface integral of doing curl dot top unit normal for this blue interior. But the curl is 0, 0, 0. Guys, what's 0, 0, 0 dotted with anything? 0. Yeah. So this entire problem reduces down to the net flow of the vector field along this closed curve is equal to 0. In fact, any closed curve for this vector field. You guys good with that? So long story short on this, Stokes Theorem, in practice, Stokes Theorem is typically a tool for finding shortcuts, and it's less good at helping us do computations. I don't know if you guys remember, but when we were doing Gauss-Green theorem, if it was like a circular region, we were like, oh, let's just do the path integral and let's parameterize that boundary. And then if our region was a square, we were like, oh, double integrals are easier. And so Gauss-Green theorem, we were kind of switching back and forth between path integrals and double integrals freely, just depending on what was an easier problem for us to do, or at least what we perceived as an easier or a harder problem. Stokes theorem, it's a little bit scarier looking of a theorem, and honestly, path integrals are typically easier to compute than surface integrals with normal vectors. And so oftentimes we use the path integral if we actually want to crunch the numbers, and we only use the surface integral if we're looking for a shortcut, like maybe the curl is equal to 0, 0, 0. So from a computational perspective, excuse me, from a computational perspective, we probably don't really want to do too many surface integrals if we can avoid it. And you can see why on the screen right now, right? If you want to do a surface integral, you have to parameterize your surface, x of st, y of st, z of st. You have to compute the curl. You have to plug the parameterization for the surface into the curl. Then you have to compute the normal vector for the surface. Then you have to take the dot product between the curl with the x of s of t, y of st, z of st plugged into it. Take the dot product of that with the normal. Then you have to do a surface integral ds dt. Not pleasant. So typically a path integral is easier. So just keep that in mind. That's just a practical thing. It's not. There's no mathematical theorem here. It's just from a computational perspective. We often find that the path integral is a little bit easier. And then, guys, last thing I want to talk about real quick are just some properties of gradient vectors. So you've seen this before, but I'm just going to refresh your memory. If we think of del as a differential operator, then the gradient of a function, you could think of that as really the vector del times the scalar f. So the scalar function f gets distributed into this vector, and the gradient of f, del f, becomes this standard definition of the gradient, if that's familiar. A couple other things that we can do here. We could take our analogies that we've done in previous chapters with surfaces and gradient vectors, and we could lift these analogies up to three-dimensional space. When we were talking about previous chapters, we would say, oh, okay, f of xy is a surface. You can think of it like a mountain, and you're going on a hike, and we could see how our height is changing as we walk on a hiking trail or whatever, right? The analogy for three-dimensional space now, we can't really talk about mountains and peaks of mountains and valleys and net change in altitude anymore. That doesn't really work. Technically, f of xyz, this would be a hypersurface. Really hard to wrap your mind around a surface living in four-dimensional space. So instead, I want you guys to think of f of xy as a temperature function. And f of xy, you're moving around in three-dimensional space, and you're keeping track of how hot or how cold it is where you are in space. So maybe you're a scuba diver, and you're like swimming in the ocean or something, and some parts of the ocean are hotter, some parts of the ocean are colder, and you're tracking your temperature as you're swimming around. And some places will be little maximums, little hot spots. Some places will be little minimums, little cold spots. And the gradient can point you in the right direction. So the gradient can point you in the direction of greatest initial temperature increase. In Mathematica, you could use the find maximum function, and that'll find the location of a little hot spot in the pool. Theoretically, you could do a little gradient field, so a three-dimensional gradient field. And if you follow those vectors, they'll get you to little hot spots. You guys good with that so far? Okay. Now in two-dimensional space, when we were looking for testing for gradient fields, we said that the rotation of the vector field had to be equal to 0. So if you had no singularities and the rotation of the vector field was equal to 0, you had a gradient in two-dimensional space. Guys, if we need an irrotational vector field in three-dimensional space, what should be equal to quote-unquote equal to 0 in this case? What's our three-dimensional version of rotation? Curl. But curl is a vector, so it can't be equal to 0. It needs to be equal to the 0 vector, or 0, 0, 0. So in this case, in three-dimensional space, a vector field is a gradient field if and only if it has no singularities, and the curl of the vector field is equal to the 0 vector, 0, 0, 0. So that's our gradient test for three-dimensional space. Here's a quick little proof in at least one direction. If you start with a surface, compute its gradient, you'll really quickly see that the curl for that gradient field has to be 0, 0, 0. If you just crunch the numbers on this determinant, you'll see it right away. So that should help there. Sorry, I just moved back slides by accident. Do you guys remember that theorem from previous chapters where we said, hey, the net flow of a gradient field along a simple closed curve is always equal to 0? Yeah, and the intuition there was, hey, let's say that you're at base camp on a hike. So you're like camping right here at the green point, and you go for a nice leisurely little hike, and then you come back to base camp. What's your net change in altitude? 0. Guess what? We have the same theorem for three-dimensional space. Now we have the scuba diving analogy, though. Guys, if you start at one part of the swimming pool and it's 70 degrees, and then you swim a little lap with your scuba gear under in the pool, and you come back to the point you started, what will the temperature be again? 70, assuming that you're in like an equilibrium state, right? So what's your net change in temperature? 0. The net flow of a gradient field along a simple closed curve in 3 dimensions is equal to 0. And there's a beautiful little Stokes Theorem proof of this. It all boils down to if you have a gradient field, the curl is equal to 0, 0, 0. And if you plug that into Stokes Theorem, that immediately derives for you that the path integral for if you have a gradient field, the path integral for that closed curve is equal to 0. Because you just plug 0, 0, 0 into Stokes for curl, and you get 0. The net flow of a gradient field along a simple closed curve is equal to 0. So if on the final exam you're asked to prove that the net flow of a gradient field along a simple closed curve is equal to 0, they're really just asking you to use Stokes Theorem. And this proof is a completely fair question to put onto the exam. Guys, I have 4 more slides. I'm going to record those, put those on YouTube for you. Maybe I'll even take this video and try to merge it with the last 4 slides. And then you should be able to see the whole lecture. Guys, especially if you're seniors and you're off for the next 2 days, you are responsible for watching those last couple slides. And you are responsible for keeping up with the try-it problems. So check the deadlines online. Those are up to date. And I do have an expectation that if you get 2 days off of school, that there will be some mathable work done outside of school.
What did you know the deadline's off the top of your head?
I don't know if it's 1 and 2 for this week, maybe.
Okay.
But it's in Schoology. It's up to date. So, all right, guys. Thank you.
Have a good, nice 2 days.
Yeah, you guys have a good 2 days off. I'll be busy, but I'll be proctoring SATs.